Okay, well, good morning, everyone. And as Eri said, it's great that you guys are here, both in person and online. So this is quite an exciting day. So over the next hour and 45 minutes, we're really going to be going through what models are available currently. And then that'll help us with discussions about where we're missing or what gaps we need to fill. So the first talk is a tag team effort from Kayla and Penny. So I'll let you guys introduce yourself and your model, but you've got 20 minutes in total, 15 minutes with five minutes of questions. Go for it.
Welcome, everyone. I'm excited to be kicking off this session. I'm going to give a brief overview of sort of VESIcal and like why it exists, why we created it and what it is. And then Penny's going to dive into the details a bit on that. So next slide, please. So the first question is, why does VESIcal exist? And you're not meant to read all of the stuff on this slide, obviously. This is just to show the absolute sort of chaos in this space of volatile modeling. Specifically, VESIcal is focused on H2O, CO2 modeling only. So that's something we can talk about as well. And what VESIcal strove to do was to make it easier to run these models. So they're all written in different ways. Some of them have Excel spreadsheets, some of them have GUIs, some of them don't have anything at all, just the equations. And not only was it difficult to run the models themselves, to test to make sure you have everything right, to run multiple samples in these models, but it was then a huge effort beyond that to compare the models together. And we wanted to make it so that you could write essentially one line of code and run all of these models and do all of the calculations you would want to do. Next slide, please. So this is just go back one. Yeah, this is just a further example of, this is actually some figures from Penny's first author paper, VESIcal Part 2, just showing all of the different little idiosyncrasies within any of these models. Some, like magmasat, have a very broad compositional range and are fully thermodynamic and have considerations sort of if you want to model things in general. Some of the other models are very specific. For example, the Allison et al. Models is sort of a amalgamation of models made for specific volcanic sensors. Some work on rhyolites, some work on basalts. So finding the best model for you was another challenge that we wanted to address with this. Next slide, please. And of course, you have to consider the pressure temperature conditions that you want to model. So really, all of these questions, which model do I use? The answer to that lies somewhere in the database underpinning each of those models. And that's in pressure, temperature, oxygen fugacity, composition space, and some other little things in the weeds. But here's an example of all of the models in VESIcal. We took 7 popular H2O CO2 models. And you can see kind of the spaces that they cover. Again, magmasat is pretty much in every way the most broad. So we have by far the highest pressure and the highest temperature and pressure range. But again, if you want to model a very specific system, you might look to one of these models that was developed specifically for that volcano. So again, it's all about how you choose the model that you want. Next slide, please. As I mentioned, composition is an important one. This is a figure that you can plot with one line of code in VESIcal. And it's showing you the database underpinning each of these models. You can plot your data on top of this to see which of these models captures the compositional space that you're interested in modeling. Next slide, please. So VESIcal is a model engine. It's not a new model. It's a way to combine all of these different models and allow you to perform an array of the calculations that you might want to perform automatically on large data sets and with any model of your choice. It's written in Python. It's completely open source. It's extensible, and we're constantly maintaining it, addressing issues, and adding new features. So there's a few goals we had when making VESIcal. Of course, combining the models into this framework was the key thing. So again, like I said, we've allowed a selection of these different models. And importantly, we spent the time Penny spent a lot of time, and our other co-author Simon spent a lot of time coding up the calibration ranges of these models into the code. So if you're using a composition, pressure, or temperature outside of the calibration range of a model that you've chosen, you will get a warning. So you can think about, is this the right model for me? We've built in automatic plotting capability, apply H2O, CO2 plots, degassing paths, all kinds of things. You can get into a sort of advanced use of VESIcal, where you can choose individual solubility, fugacity, and activity models that you can interchange, and you can hybridize models. So let's say you have you want to use the Dixon model, which is underpinning VolatileCalc, but you want to use a different equation of state to see how that affects the results. That's something you can do with VESIcal. Like I said, it's open source and extensible. And one really important thing to us, which is becoming more and more apparent that this is critical in this age of modeling, is that we wanted this tool to be highly usable to people of all skill levels. So next slide, please. So that we've hopefully achieved that in a number of ways. This figure is a bit complicated. Again, you don't need to read all of it, but this is just showing the general way that the code itself is used. So if you're a Python coder, like I said, you can use it in a very simple way where you upload an Excel file, write one line of code to do your calculation, and get a new Excel file back out. You can also dive deeper. So this is sort of the glacier here with the easy stuff at the top, and then the more complex stuff hidden under the water, where you can, again, interchange models, hybridize them, run your own code. There's even ways to add your own functions to the existing models. Next slide, please. And also, we've gone all the way down. We say, what if you don't even want to touch Python? We'd love you to, but let's get you started using this model. So we have a web app. We can upload an Excel file and do any of the calculations you want. Again, it's not, you can't dive in as deep, but you run all the models you want. Next, please. We have a number of Jupyter notebooks. In fact, the manuscript, VESIcal Part 1, is not only written in the standard PDF format, but is also entirely written in a Jupyter notebook that you can run through a binder, which means you don't need to install anything. You can run it in your web browser, and you can execute the code that shows you examples of every function, at least the ones at the time of publication within VESIcal. Next, please. And critically, we have what I think is very, very thorough documentation of VESIcal that we're adding to all the time. So we have this read the docs page, and all of these things are linked in the manuscript. So we have a complete reference to all the code functions. We have examples. We have YouTube tutorials. We have images and documents from presentations we've given, and ways that you can get support and ask questions. Next slide, please. So into the actual bones of this thing, what do you want to do, and what might you want to do with VESIcal? So these are the 5 what we call core calculations that we developed for VESIcal. And so all of these are their own function. You can calculate the dissolved volatiles in a particular magma. You can calculate the equilibrium fluid composition at volatile saturation, calculate the saturation pressure. So this is the melt inclusion enthusiasts in the room will like that one. You can calculate isobars and isoplots with any of the models and automatically plot them. And you can calculate degassing paths and automatically plot them. Next slide. Like I've alluded to earlier, you can create your own functions, and we've had a user do this, and there's an example of that on the Read the Docs. You might want to do something a little bit different, tweak one of these, and you absolutely can write your own code, and you basically duplicate one of the existing models, write your own function, and it goes and it grabs the fugacity model, the activity model, everything you need automatically to run your own calculation inside someone else's model. Next slide. All right, go ahead, Penny, please.
Okay, so I'm going to talk a little bit about kind of the history of the models that we included in VESIcal. So you can kind of think of the evolution of volatile solubility modeling a bit like this manuscript before and after peer review. So kind of in the like 80s and 90s, you had a relatively simple model. And then sort of from the 2000s onwards, these models have got much more complicated. They've started including non-ideality. Specifically, the early models, as you add water, the CO2 solubility drops, kind of assuming it's following Henry's law. Whereas now a lot of the models, as you add a small amount of water, your CO2 solubility initially increases and then starts decreasing again. And this causes greatly different isobar shapes when you plot them up. They've also, in general, become more thermodynamic, including integration with thermodynamic packages like melts. We've had to start including more and more complex terms for melt composition, and this is simply as the calibration range has expanded. So as we've moved from basalts to including andesites and rhyolites, basically now the models use every single melt oxide that you would measure on a microprobe. And then kind of the final frontier, which is not addressed in VESIcal, is other fluid species. So at the moment, none of the models do chlorine, sulfur, or fluorine. So I'm going to go through the models in kind of chronological order and to kind of show how technology has advanced, and with the tools we're using for these models, I'm showing the most popular cell phone the year the model was released. So in 1997, Jackie Dixon released her seminal work looking at the solubility of these 5 different compositions. So relatively low silica and varying alkali contents. And what she showed is at a given temperature, obviously CO2 solubility increases with increasing pressure, but that the slope that this takes is highly dependent on the melt composition. So the lucitite dissolves far more CO2 than the Rheolite at a given pressure. So she parameterized this in terms of this pi term. So this is the cation fractions of silica, aluminum, calcium, potassium, etc. And as this pi term increases, CO2 solubility increases. However, she was specifically interested in solubility in a suite of lavas from the North Arch volcanic field that's near Hawaii. And what she found in that suite is that this pi parameter, which is relatively complicated to calculate, actually correlates very well with silica content. And this meant for this suite of lavas, they could simplify the model. So instead of having to include pi, they simply, the only effect of melt composition on volatile solubility was silica. And this produces the form of the model that almost all of us will have used. So it's quite thermodynamic mostly. So you basically have the solubility of carbonate on the left-hand side and molecular water down below. All of the terms right of the circle are kind of your thermodynamic terms. And then you have this sort of empirical correction term. So basically this is the only thing that accounts for melt composition. So this basically corrects the amount of carbonate that dissolves for the silica content in the liquid, and the same for the water solubility. So this is really a simplification of the true Dixon model. You will see in the literature, some people say they're using Dixon with the full pi term, and others are just using this simplification. And it's this simplification that was included in VolatileCalc. So VolatileCalc was an Excel spreadsheet published in 2002. You can see we have a substantial increase in computation ability here. And basically, Sally Newman and Jake Lowenstern coded up 2 specific models. This is what it looks like. Many of you will have interacted with it. And the Rheolite functions use various different parameters from Stoper and Fogel and Rutherford. This is an old model. It's not in VESIcal. But what's key is the basalt model of VolatileCalc is basically Dixon. It is Dixon with the silica simplification. So that is why when you go to calculate a saturation pressure in VolatileCalc, it is only asking for the silica content. It's because it's using that empirical parameterization I showed on the previous slide. What does that mean? It basically means you are assuming that your lavas have the same pi-silica relationships as the North Arch lavas if you're just entering silica content. You're assuming silica content is a proxy for how much water and CO2 can dissolve. And this works very well in some systems. If you were to plot your melt inclusion data on top of the pi-silica relationship that they parameterize, and they lie there, this is a reasonable assumption. Where it goes wrong is if your lavas look like this. And this is what we see at Kilauea volcano. So at a given silica content, your pi value is actually higher than the North Arch lavas. And that means that it should have a different solubility, and yet you're basically assuming it lies on this line. Another simplification of VolatileCalc that is also in VESIcal is once you start going to higher silica contents than the North Arch lavas have, eventually you would end up with a negative pi value. And that would cause you to have negative CO2 solubility. So the spreadsheet doesn't allow you to enter a silica content more than 49. It will basically use the pi value for 49% silica. So if you have melt inclusions between 49 and 53 weight % silica, the model isn't using any change in those melt compositions. It's having to use a fixed CO2 solubility. So this is worth understanding as a limitation of this model. In 1998, Gordon Moore released a water model that covers a much larger range of silica content than VolatileCalc. This model has a relatively simple formulation. So it's empirical. You basically have dissolved water on the left-hand side, some pressure, temperature terms, a term for the fugacity of water. And this means, although this model doesn't have CO2 solubility, this allows you to combine it with different CO2 models. So in VESIcal, you could take the Dixon 1997 CO2 model and use it with more if you wanted to. This model has a lot more terms for melt composition. And you can see that here in this summed term. So basically you're taking the amount of aluminum, iron, and sodium in your melt, and you're multiplying it by a constant. And that is what is controlling how much water your melt can dissolve at a given pressure and temperature. Then in 2005, Lou comes along and does some experiments in Rheolite. So that greatly extends your silica content higher. This model is fully empirical again, and it has no term for melt composition. So whenever you use this model, only your pressure and temperature are affecting how much volatiles are dissolved. It doesn't matter what your melt is. It's basically just got a lot of pressure over temperature terms raised to varying powers, which give it this shape in solubility pressure space. But one of the key things about this model is it has non-ideality. So it shows curved isobar shapes. And this is one of the first models to do this. Then Icone and Marciano come along and they greatly extend the silica content upwards. So you can see we have a lot more silica-rich basalt, higher sodium and potassium contents. I'm not going to go in too much into how this is, but I will share these slides. Then Shishkina came along and did a lot more experiments at higher alkali contents. And this is another empirical model. And then kind of the big model Magnus comes along. This was supposed to be internally consistent with Rhyolite melts. And you can see this uses a huge range of melt compositions. So we're no longer working in just basalt space or Rhyolite space. We're kind of crossing the whole of compositional space. This does mean it's more complicated to understand than these thermodynamic models. So instead of using times by the mole fraction of magnesium or calcium, it has these kind of terms for interaction parameters with different melt oxides. And the key thing to appreciate here is this model includes speciation. So this is the first model that doesn't do total CO2. It does carbonate and molecular CO2 as well as water. So we'll wrap that up there, and I will share these slides if you want more detail on the rest of these models.
Thanks, Penny. Sorry for giving you the hurry up there, but I did want people to have time for questions because I suspect there might be a few. So we have about 3 or 4 minutes for questions. Okay. Oh, Ari's got one.
How long does it take to run, I don't know, if you had 50 melt inclusions to run the saturation pressure calculations, how long would that take to set up and run?
So that would be just a couple lines of code. So setting it up would be relatively quickly. But actually running it really depends on what model you're using. Magmasat takes longer than any other model because it's having to iterate several times for each sample. The other models, because they're simpler, take a fraction of a second for each sample. So a second you could run probably 50 melt inclusions.
On a 16 gig laptop, Magmasat takes about a second per melt inclusion if you run it on Mark's Enki server. If you install VESIcal locally and on a bigger, more powerful computer, you can run it much faster than that. So it is kind of a function of how much RAM you have and processing power.
Thank you.
We got a question here from John. So.
where do you see this model engine going in the next few years? What are the key things that you would like to add, modify, improve in your engine?
I mean, I think the elephant in the room, which will become apparent throughout the rest of this workshop, is sulfur. Sulfur is, our biggest connection to volcanic degassing. It's the easiest to measure at volcanoes, and making that connection is going to be critical. And so Penny and I have been talking a lot. That was always our biggest wish for VESIcal 2.0, was to add sulfur. Since we've published, so we've also added a few other things. We've added the ability to calculate melt viscosity, melt density, and some other things like that. So a lot of little tweaks, but I think sulfur is the biggest one, and eventually the other melt species, and just, sort of keeping up with the literature as we discover more and more.
The other thing is we are making it easier to install locally. So at the moment, if you're on Windows, you have to run it on the Enki server. And that's because it relies on like the underlying melt infrastructure thermo engine, which currently can't be installed on Windows easily. So the aim overall is eventually Mark will put this on pip, which is a way of distributing Python packages. That's how VESIcal is distributed. But that's kind of like the frontier to, if you have a fancy Windows desktop, to do that easily. You can do it at the moment through Docker and other things, but that would be the 5-year dream, is that it's easier to install on Windows.
Absolutely. And I'll just note that if you install VESIcal now and you don't have a thermal engine, which is melts, installed, you can run all of the other models. You just can't run magmasat, which most of the time magmasat is what you want to be using. So yeah, that's a big goal for us.
Okay, thanks very much for the tag team there. It was really well done. Well kept to time, thank you. I know that Penny could have talked for a lot longer on the history of cell phones.